Okay, good day. This is AP Calculus. I am Mr. McCulley, and this is section 4.6 Numerical Integration. This is the last section in chapter 4, so let's get to it. All right, so numerical integration. We're going to be approximating a definite integral using the trapezoidal rule. The good news is that anytime that you are asked to do the Simpsons rule, you're allowed to skip that in the homework. And I won't be asking it on a quiz, but when you're doing the practice work, wherever it says do it both by the trapezoidal rule and Simpson's rule, skip the Simpson's rule, just do it the trapezoidal rule. And then we're going to talk about how much error there is in the trapezoidal rule. Okay, so trapezoidal rule, what does that do? Well, before we get to the trapezoidal rule, we got to say something about integration in general. Now, in the quote-unquote real world, if you're asked to integrate a function, there's actually a pretty good chance that you won't be able to integrate it. And so you have to come up with some sort of numerical approximation for that integral. And, graphing calculators do a great job of doing definite integrals. But classically, the trapezoidal rule is one way that you can come up with a fairly decent approximation of the the integral or the area under the curve. So the trapezoidal rule is a method that approximates area. And so if f is a continuous function over the interval from a to b, then the definite integral can be approximated by this function. So here is my definite integral, and here is an equation that we can use to actually make that approximation. Now this equation here, it doesn't look like it, but it is very much related to, excuse me, the classic area of a trapezoid equation, which is a equals 1/2 h times b1 plus b2. Now you can't really see it here, but this 2 on the bottom represents this half. This b minus a over n is going, and I'm going to show this on the next page, but it represents the height of every one of these trapezoids, and it's going to be consistent. And then these things are going to f of x sub 0, 2f of x sub 1, dot, 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 all the way up to just plus 1f of x sub n is going to represent the multiple bases that are going to come from drawing in our trapezoids. Okay, let's cancel this. I don't know why that comes up while I'm trying to record a video, but let's move on. Okay, so a visual representation of the trapezoidal rule, and I erased it, and let's see here. I just want to, let's draw in, and you know what? No problem. We'll fix this real quick. Let's just select this and delete this. Okay, we'll edit it in post maybe. Okay, so let's draw this in here. So let's say I want to find the area under this curve from A to say B. And again, we're keeping it simple. This is my function f of x. And so let's say let's use 3 intervals. So our n equal to 3. So let's draw in 3 trapezoids, and we're just doing 3 trapezoids to keep it simple, but we can use as many as we want. And the more trapezoids that we use, the better the approximation. So let's see here. That's not too bad. I probably could move this one over a little bit. But let's just, for the sake of argument, assume that all of these are equal intervals, and I divided them into 3. So this will be x sub 0, and this one here will be x sub 1, this one here will be x sub 2, and this one here will be x sub 3. And so A is x sub 0 and B is x sub 3. Not too bad. But if I want to find the length of this thing, so the length of an interval, it's going to be b minus a divided by 3. Because to find the length, I go b minus a and I divide it by 3. That's pretty straightforward. Now this height, how do I figure out that height? Well, I plug in the x value. So this height right here is f of x sub 0. This height here would be f of x sub 2, or excuse me, 1. Don't make that mistake. F of x sub 2 goes there, and this one is f of x sub 3. Okay, so remembering that the area of a trapezoid is 1/2 the height times b1 plus b2. So the first thing we want to do is say that this definite integral is going to be approximated by the area under the curve for these three trapezoids. And so it looks like we're going to get a fairly reasonable approximation. We're going to be a little over on this trapezoid. This one looks almost exact. We'll be a little bit above. So our approximation should be pretty good for at least for this one. And we go from a to b of just this function f of x dx. Again, f is going to accumulate all the area under that curve. And so if I apply this area of a trapezoid equation to this first trapezoid right here, I'm going to get, it's going to be 1/2 and then the length of an interval, which will be the height. And again, it's going to be the height because I have right angles here and here. And so I've got vertical parallel lines for the trapezoid. And I know in geometry, they usually give the parallel lines of a trapezoid horizontally, but in this case, we just kind of have to twist our head. We'll get there. And so it is b minus a over 3, that's that height, and then it's going to be f of x sub 0 plus f of x sub 1, and then that's this length right here, and it's going to be that length right there, because the distance from 0 to the point on the curve is that height. Okay, so now for this trapezoid right here, we're going to have basically the same starting point, because again, we've divided this into equal intervals. So again, it's going to be b minus a all over 3. But this one's, its bases are f of x sub 2 and f of x sub 3. All right, and so this last one here is going to be 1/2 again, and then it's going to have the same b minus a all over 3, and then its bases are going to be, for this one here, it'll be this base f of x sub 2 and f of x sub 3, so f of x sub 2 and then f of x sub 3. Now when I look at this thing, I see basically 3 terms. I see this value here, this value here, and this value here. They're all added together. And so what we can do is, if I look at it, they all have a factor of 1/2 times b minus a over 3, 1/2 b minus a over 3, 1/2 b minus a over 3. So let's factor that out. Let's put the 1/2 together. So it'll be b minus a over 2 times 3, and I know that's 6, but I want to keep it so that I can refer back to the equation we had in the last one. So I'm going to keep it as 2 minus 3 there, or 2 times 3. And then when I factor that out of these terms, so if we look at it, I'm factoring it out of here, I'm factoring it out here, and I'm factoring it out there. And so what will be left is f of x sub 0 plus f of x sub 1 plus crud. I made a mistake, didn't I? Because I got the two same things here. You guys are all yelling at me. Macaulay, you're dumb. You keep making the same mistakes. Okay, so we'll fix it. We'll fix it. Look, this one's f of x sub 1, f of x sub 2. This is supposed to be the middle trapezoid, so we can fix it real quick. We'll just say this is f of x sub 1, and this is f of x sub 2. F of x sub 1, and this is f of x sub 2. And it should be right, because again, this is f of x sub 1, that leg, and this is f of x sub 2, that leg, and then we'll do it right. Okay, so got it right now. Hopefully you see where my mistake was and you're just laughing at me. That's okay. F of x sub 2, and then f of x sub 3. So this looks right, and again, this I'm just rewriting here. And so let's get rid of the highlighter. So this one is right here, this one right here is there, and that one right there goes there. So we've got it all squared away and straightened out. Now what you'll notice is that these two here in the middle are repeated. So I've got b minus a all over 2 times 3, and then I got f of x sub 0 plus 2f of x sub 1 plus 2f of x sub 2 plus f of x sub 3. So the reason that when we look at this trapezoidal rule, this generalized equation, the outside is just 1, and then all these inner values have a scalar factor of 2, wherein the outside one, again, or the last one, only has a factor of 1 there in front. It's because when you separate all of these, when you factor out the half and then the height, you're left with using the inner bases twice. The outside base only gets used once on the first trapezoid, whereas this second base gets used twice in the first trapezoid and the second trapezoid. That's why it becomes a 2. This second one, or this third one actually, third base here, ends up being used in the second trapezoid and the third trapezoid, and then this last base right here only gets used once in the last trapezoid. So that's why the first and the last one only have a factor of 2 in them. So we could figure that out. Now let's go ahead and calculate that. And oh, I don't have anything to calculate. I'm just, again, trying to show you why this expression ends up working. So let's actually try one. So this says is an example from page 316. It's number 4, and they want us to find use the trapezoidal rule to approximate the area under the curve from 2 to 3 of this 2 over x to the third. All right, now this is one that we could actually do numerically, but again, we want our n to be equal to 4, and so what we're going to end up doing is figuring out some values. So if I do that, if I divide it into 4 equal parts, we'll say x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. So I have the distance between these two is 1 interval, the distance between those two is 2 intervals, the distance between those 3. And so I know what the endpoints are. It's got to be 2 for the first one, and it's got to be 3 for the third one. Now I just got to divide it up into equal parts. Now halfway between 2 and 3 is going to be 2.5. That's good because I'm halfway in between those. And then halfway between 2 and 2.5 is going to be 2.25. And then halfway between 2.5 and 3 is going to be 2.75. So that's how I've determined my intervals. And you can do that for anything if you wanted to. Just subtract, divide by that number, and then just add it. So if I go 3 minus 2, that's going to be 1. 1 divided by 4 is a quarter. 2 plus a quarter is 2.25, and then 2.25 plus a quarter is a half, or 2.5, and so on. So you get an idea. Now, I don't have my graphing calculator emulator here at home when I'm making this. And this is a 0, not a 6. So I got to find f of x sub 0, f of x sub 1, f of x sub 2, f of x sub 3, and then f of x sub 4. And you're AP Calculus students, and you've been using the graphing calculator since at least Algebra 2. Hopefully you got one in geometry, but I don't know. So anyway, you guys know how to make a table. Our equation is just 2 divided by x squared, and, x to the third. Do it right there, Macaulay. And so we could just plug it into our graphing calculator, and is it x to the third? It's not, but we'll deal with it there like that. X to the third. So what we can do is we can put that in our graphing calculator, make a table, go to our table setup. We're going to start at 2. We're going to go by 0.25. We're going to turn everything to auto, make our table, and so f of x sub 0, it is going to be 0.25. This one's going to be 0.1, and I'm going to have to round it. You could use more exact values, but 1.76, and then this one is going to be 0.128, and then this one is 0.0961. We'll do 3 significant figures, and then at 3 it's going to be 0.0741. Those are our values there. Okay. So this integral from 2 to 3 of 2 over x to the third dx is going to be approximated by, all right, so I need b minus a, which is 3 minus 2 over 2 times the number of intervals, which is 4, and then it's going to be just 1 of the first one, f of x sub 0, so it's going to be 0.25 plus 2 times 0.176 plus 2 times 0.128 plus 2 times 0.0961, and then since this is the last one, we'd only go 1 times that, which would be 0.0741. 61 plus 0.0741. Okay, so I get 1 over 8, so I get an eighth there. And then again, I'm just going to grab my calculator and calculate this quickly. 0.25 plus 2 times 0.176 plus 2 times 0.128 plus 2 times 0.0961 plus 0.0741. Let's hope I typed all that in correctly. And then that divided, so just, you may have to check me. 243 is what I got there. So when I multiply that times 1/8, or just divide by 8 there for my answer. Let's delete that. I get 0.141. That is my area under the curve. Okay. And obviously it's going to be small because, again, we know what the shape of this graph is going to look like. And when x to the third is between 2 and 3 there, 2 to the third is 8. So it's going to start, 2 to the third is 8. It's going to start at a quarter right there. And then when we go down to here, 3 to the third is a 27th. So we'll get 1 over 27 right here. It's going to be really, really short. So we don't have a whole lot going on in between here. So 0.14 seems like at least a reasonable area for the area under that curve. Okay. Finally, let's talk about approximation for error under the trapezoidal rule. So this is a calculation of error for us. And this is a approximation of the maximum amount of error you could possibly get underneath the curve for this, just depending. So again, the b minus a is pretty straightforward. It's just the upper and lower limit. N is the number of intervals that you use. This right here, though, is new notation. And so it says what is the maximum value of the second derivative over this interval. So let's talk about the maximum value of the second derivative. Well, for the one that we just did here, so this one here, we want to know about how much, what is the maximum that this could possibly be off. All right, so, well, if I take the second derivative, if I go f of x, and f of x was 2 over x to the third, which I could rewrite as 2x to the negative third, right? So if I take the first derivative of that, I get x, and then again, it'll be, I'll bring down the 3, so I'll get negative 6x to the negative fourth, and then the second derivative of that would be x equals, and multiply those two, I'll get positive 24x to the fifth. To the negative fifth, I'm sorry, because I got to reduce it by 1, which again I can rewrite as 24 over x to the fifth. Now, to find the maximum value of that thing, remember, you could find a maximum or minimum by finding the critical numbers of the first derivative. And so this should be second derivative. But what we could do is we could say, all right, I could take a derivative again and find the critical numbers and then test those points. But if I look at this thing here, it's almost exactly the same shape except smaller than the shape of the original, because look, when I do this thing, let's go back to here. When I plug in 2, I'll have 24 over 2 to the 5th. All right, whatever that is, 2 to the 5th is 32, and then it'll be 24 over 3 to the 5th, and 3 to the 5th is, let's see here, 3 to the 3rd is 81, 3 to the 5th would be 243, something like that. So obviously it's going to again go like this. So we could spend a lot of time finding out the maximum, and we know that the maximum over the interval could occur at an endpoint, but we know it's here. And you know, if it's uncertain, you may have to take another derivative and find critical numbers of that. But in this case, we don't have to do that. So the error for this expression, this is total error, it has to be less than or equal to, in this case it'll be 3 minus 2 now to the 3rd over 12. We used 4 intervals, so 4 squared, and so the maximum, this thing here is going to be maximized at f double prime of 2. So I get 1 over 16, that's 12 times 16, and let's see here, the double prime of f2 will be 24 over, let's see here, 2 to the 5th. Let's see here, 2 to the 5th. I said it's 32, right? So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So I got 32 there. Now, let's see here. Let's multiply this out. I can cancel out a 12. That'll leave me with a 2. So I'll have 2 on the top, but I can cancel out 2 with an 8 there. So that'll be just a 1 now. So 32 times 8, I can't do that in my head. I should be able to. 32 times 8 real quick. And 256, yeah, I should have known that. 256. So the maximum amount of total error that can be, and this should be less than or equal to. So my error, the absolute value of my error has to be less than or equal to 1 over 256. Well, that's generally it for this particular section. It's pretty short, so we are done, folks. We are to the Star Wars fun fact of the day, and this one comes from the Star Wars TV series called Star Wars Rebels. And if you're not watching Star Wars Rebels, you should be. It is by far the best TV series that Star Wars has ever produced, and it is talking about this guy here. He is not necessarily a Jedi Knight. He was a Padawan during Order 66. If you don't know what Order 66 is, shame on you. It is the order that Emperor Palpatine issued to kill all of the Jedi, and he was just a Padawan at the time. His master, a Jedi Knight who sacrificed himself during the Order of 66 so that Kanan Jarrus could get away. And Kanan Jarrus' real name, that is the trivia fact of the day, is Caleb Doom, or maybe Dume. I'm not real sure. I didn't know how to pronounce it, but we find that out in the canon novel A New Dawn. All right, folks, you have a great day and enjoy the rest of your break. Have a good one. Bye.